Okay. So I am going to present on the portion of the project that was a transportation use case. And there were a couple of transportation use cases, but this is the one that we worked on at NREL, and it corresponds with the GEMINI XFC project. So that project was basically examining fast charging around a synthetic version of the San Francisco Bay Area and how that would affect distribution systems. So a basic layout for the project is that we had PyDSS for the grid simulator. So that's an in-house NREL. Can you guys see my mouse, or should I just not bother with it?
I think we can see it, but it might be delayed. So
Oh, okay.
yeah, but so if
So
slow movements will work.
okay, cool. So PyDSS is the grid simulator. So that's something developed in-house primarily by Adel Latif at NREL. But it's a flexible simulator that can handle lots of high adoption cases for solar and storage and do some pretty great things with inverter models. And excuse me, especially for this project, it was really useful because it has a built-in Helix interface. So then that connected to a distributed energy resource management system, a DERMS. So the DERMS was basically something that would take the voltage measurements from PyDSS and create a voltage load sensitivity matrix and establish load limits for each of the sites where the charging stations were. So if you had lots of charging going along all of the feeder, maybe some of the charging stations downstream would have a maximum load limit provided to them. Then at the center of our co-simulation was a site power management controller. So what that did was take the load limits from the DERMS and distribute them amongst the chargers at the station. So if you can imagine a row of cars charging, and they all have expected leave times and expected charging amounts, it would try to meet as many of the charging demands within the time allotted as possible, instead of just a standard, first come, first serve type of setup. It would also control some co-located energy storage. So some of the larger charging stations had energy storage placed with them. And so that would help manage if there was a low limit coming from the DERMS, then maybe they could pull from the or from the energy storage to still charge the vehicles how they needed. And then the signal from the site power management controller would end up at BEAM. And BEAM is a very in-depth transportation simulation created at Lawrence Berkeley National Lab. So that one models vehicle travel. Well, it models many modes of travel, but the one that we were tracking here was vehicle travel, and especially the electric vehicles within that vehicle set. And so then Beam would receive a signal saying, okay, these cars charged this amount, and it would adjust its routing and its scheduling accordingly, because it would make sure that the vehicles went to charge before they ran out of power and might divert a vehicle mid-route if it needed to charge on the way. So this overarching model fit into Helix pretty well because we had many different vetted tools that we wanted to put together, but didn't innately support each other. So instead of having one big thing, we had co-simulation between established smaller things. So a couple things that are enabled, especially in the latest version of Helix, is that Beam was created to run easily on the Amazon Web Services nodes. So that one we maintained and continued to run on AWS, while PyDSS was created to run more easily on NREL's in-house. Well, it can run for small simulations on a desktop, but once we scaled up, I configured it to run more easily on NREL's in-house high-performance computer, so on Eagle. And Helix was able to bridge those different platforms. So Helix allows not only different machines to run different simulations, but it also allows running across different operating systems, which is really helpful. Another element that Helix enabled is that PyDSS was memory intensive to model the whole San Francisco Bay Area. So what we did was we broke it down into different regions. And so each instance of PyDSS might run a subset of feeders, and then within that region, they would communicate with and connect to each other, where the feeders would take a feed-in voltage from the subtransmission module, and the subtransmission would take a net load. And so we would have co-iteration there to make sure that there was convergence as if it were running as one big model. But breaking it down just allowed us to parallelize a little bit better and spread across nodes on Eagle to spread out the memory demand. So that was enabled easily through a broker hierarchy. So we would have one broker that would handle a region, and then that broker would send signals, if any were needed, up the chain to a master broker. And then the master broker is what coordinated between Beam on AWS and PyDSS on Eagle. So then another crucial step was to create a firewall exception. So although Helix allows communication across platforms, our IT security doesn't innately support that to our HPC. So I had to contact them and let them know, like, look, we're going to be communicating back and forth between this node and that node. I trust this source because it's me, so please allow it. And so we created that firewall exception, and it was one thing that can help smooth that out if you're trying to do something similar is if you specify a set of sockets or a socket that it will be connecting to, then that's a little bit more secure than saying, well, I'm not sure where it's going to connect. Can you just open this huge range? Because then if something else connects in that huge range, you don't really have the security any longer. So because we knew where the messages were going to be coming from, we could use a ZMQ-SS, so single socket type connection. And then we could specify which ports, and that helped speed things along. So as far as the message passing, Beam, which is our transportation model, publishes a large JSON string that includes all of the charging demands for all of the vehicles at the moment. So that happens for two reasons. The first being that it's easier to debug one publication subscription connection rather than millions. And so I just needed to make sure that that one publication subscription aligned and we were good to go. The other piece of that is that it was easier to allow it through our firewall if we had one large publication rather than something that looks very similar and comes very rapidly many, many times. That looks like you're just kind of like spamming something. So we had the one large publication specifying the vehicles, which charging station they were at, and then the load that they were demanding. Then at the master broker level, so at the top of my broker hierarchy, I had a federate connected that was an intermediate federate that could parse that large publication because I didn't want all of the data going to every single feeder. That became kind of memory intensive. I just needed some of the charging stations. So whichever charging stations were at a specific feeder needed to go to that one, but not all of them. So I had an intermediate federate that parsed and separated those into different distribution federate messages. So I already described the nodal voltage and nodal load publication subscription. That's just internal to the distribution system to make sure that you have that co-iteration and convergence as if it's running as one big model, even though it's running across multiple. And then the distributed energy resource management system that was creating the charging limits, that subscribed to those nodal voltages as well, and used that in a voltage load sensitivity matrix to create max loads while maintaining your voltage level within ANSI limits. Finally, the SPMC, so that centerpiece that coordinated the charging control and the distribution response, that took that desired power from beam and the charging limits from the DERMS and figured out how to best accommodate as much charging as possible while still meeting those limits. And then dispatching the storage as well. So here's some results from one of our preliminary studies. So again, this study was really made possible from some of the features allowing scalability through Helix. So we modeled the Bay Area. So this is the range you're going. If this is San Francisco, you're going almost east to Sacramento and pretty far north and south. And then for more in-depth studies, we focused in on Oakland and Alameda, so this little area across the bay. And the reason we chose that is that it has a few rural areas as you get closer to Parkland. And then it has suburban, and then down in Oakland, there's like some more high density downtown areas, as well as industrial loads for ports and things like that. So what we did is we focused it on Oakland and Alameda to look at some more in-depth processing because we were doing some analysis down to individual customer level, individual charging stations. Each individual person's travel trip itinerary was tracked in Beam. So this extremely high resolution became a little unwieldy to process. So for some of our more in-depth analysis, we focused down. And what you're seeing basically is not much charging at midnight, some charging in the morning as people head to work, a little bit at the noontime rush, like for lunch, and then a bunch is more out into the suburbs as people get home after work.
Just heads up, we should try to wrap up in the next minute or two.
Yep. So thanks for the warning. So on the grid, basically what that's doing is before charging, because of all the solar and storage that we expect in the same time frame as this high level of charging, there's some higher voltages on our system. But then once we add some charging loads, if we don't control it, we see feeders that can't support that load at all, and some feeders out into the suburbs that have low voltage, but you don't see voltage collapse yet. So still not good, but not quite as impacted as the downtown Oakland area. So we're continuing this analysis with tuning some different controls to see if we can get the with charging picture to look a little bit more like the without charging picture. But that's in some future publications. But yeah, we worked with the Helix team and got some really great scalable features. So if you're looking to scale a project, I suggest reaching out because this team can really help facilitate that and bring some models close together.
Awesome. Thanks so much, Nadia. We do have some time for questions before we switch presenters above the hour. So go ahead and ask away. All right, if you want, you can always put stuff in chat. Feel free to raise your hand or speak up if you'd like as well too.
Hi, Shin. Nice to see
Hi.
you.
Hi, Nadia. I do have a question. So in the grid simulation, right now it only has the distribution grid, right? Do you have
Yes.
any transmission level simulation like power flow or generation scheduling?
Yeah, so we have some subtransmission, but we don't have any generation scheduling, and it's not a T&D co-simulation.
Okay.
There is some work that we're working with Otto on larger co-simulation. So it takes this work, little pieces from it, not the full scale. So like a feeder and then a small little version of beam, and connects it with some transportation or some transmission models that he has. And
Okay.
so that does co-simulation and co-iteration, but that's still in the works. But yeah, it's to do that at scale would be even more challenging, I think, especially because a lot of the transmission models,
Okay.
when they're considering generation, don't consider power flow. So that's a
Okay.
challenge. But I know that the one that Otto is working with, he's using a power world model that will do power flow, so we can take that feed-in voltage. But it doesn't do generation scheduling, so there's a trade-off.
Okay. Yeah. Second question is, what's the size of the distribution system in that region right now? How many like distributing node in the simulation?
Oh, how many nodes?
Mm.
Maybe Brian knows the answer to this one a little better.
Yeah, wait, so this is for those two, the number I know off the top of my head is the full San Francisco Bay Area, which was the one that was run for some of these results, and that's right around 10 million electric nodes.
Okay.
For
Good.
power simulation. Those SmartDS data sets. Oklahoma Alameda is one of the largest of the 40 regions there. So,
Yeah.
I don't know, divide by 20, or something, get close. So still quite big.
Okay.
And then it's a similar order of magnitude for charging. Some of our higher charging scenarios have like 7 or 8 million charging stations across that area. So it's pretty large scale on both ends.
Okay. Great. Thank you, Nadia. Great to see your work.
Great
Yeah,
to
thanks.
see you, and great questions. One thing I might add, I happen to have been a little bit involved with this project as well, is that to your original question around the transmission side, for the questions at hand here, the real focus was on the impacts of distribution. But there was some consideration given to what the sort of transmission generation mix would be, just kind of exogenously, like we weren't looking at interactions there. But
Yeah.
the idea of understanding, okay, what types of grabbing from the standard scenarios, for example, and using those as an idea of what the generation profiles might look like, and letting that impact things. It wasn't necessarily impacting the physics, so that wasn't a core focus.
Okay.
Other questions for Nadia?
So I saw a message from Jing that's saying that the San Francisco Bay Area has 10,000 plus nodes, but that must be just for downtown San Francisco, right?
Yeah, for autonomous energy system, we have done 10,000 nodes. Yeah, it's that Bay Area.
Okay. Yeah, so maybe different models capture different spaces.
Okay. I think this is great work, and looking forward to see more results. Yeah.
Great, thanks. We have one paper published from this that shows similar results to what I've shown here, but we're working on another one that shows some impacts of the controllers and how that can maybe mitigate some of those outages or low voltage scenarios.
Can you post your paper in the chat window so we can take a look?
Yeah.
Thank you. Yeah.
And the second one that Nadia mentioned is like often reviewed, so we're hoping that soon we'll have other things to share. I'll ask a general question. just as we're kind of winding down here, is, where do you see kind of as next steps or opportunities to go beyond what was done here to either answer other questions or things like that?
Yeah, so I definitely think the control system has some viability. I'd like to explore some of the charging station placement impacts, because we realized along the way in this project that we would get very different results depending on where we put the charging stations, and Beam wouldn't necessarily show different results if a charging station was a block away, but that block away might be on a totally different feeder. It might have a shorter connection to a higher voltage line. So it had huge impacts on the distribution system. And that wasn't really originally part of the scope of this project to explore that placement, but I think that that's like really a critical way to go about it. So if we could make a flow where people could have, or I guess utilities could have, and then their customers could have access to a hosting capacity chart similar to the hosting capacity charts at PG&E for solar. So a customer can just pull up their map and see, oh, I probably won't get approved for solar right now. Or they'll pull it up maybe a year later, see that some upgrades have been done and say, oh, now I can get it. If that could happen for charging, that could speed along these high density fast charging stations, so that then the developer could pull up a chart and say, oh, well, we kind of wanted it on this block, but if we move it down the street, then we could connect that much faster. So having something like that could really further this technology advancement a lot faster. So if we could explore the placement strategies, I think that could be a really cool insight.
Yeah, that's great. Very cool. Got about a minute left here. Any last quick comments or questions for Nadia?
Hey, Nadia, this is Andrew. I'm wondering if you could speak a little bit about the upgrade strategy or challenges in such a large area for this kind of simulation.
Yeah, so Andrew's getting at a piece of the project I didn't really present on here because we didn't use Helix too much for this part. But there's a tool at NREL called DISCO, and it's the distribution. Oh, I'm missing some letters, but it's a cost analysis of upgrades for distribution systems to improve their thermal loadings and their voltage regulation. So basically, in some of the scenarios, we saw charging to the point where I wasn't able to get a converged solution for the power flow. There was just a lot of load that was very challenging to meet. And so we explored upgrades for transformer upgrades, line upgrades, adding voltage regulators, adding capacitors to be able to support those increased loads. And as you can imagine, with the higher charging scenarios, you see a higher cost of those upgrades. But it's a balance, right? So you can limit some of your charging or control it and dispatch it and make sure that everyone's tuned into this control network. Or you can pay to kind of bulk up your grid to allow for those larger charging loads. So we're exploring that a little bit further to see what that balance is, because we know there's generally a trade-off, but if we can quantify that a little bit better, then that could be a little bit more a little bit more of a guidance towards developers and utilities on what kind of balance they wanted to strike. Yeah, I think I see Shivani's hand, which is great because she's helped with some of that upgrade analysis for other projects. But
the only thing is I'm going to have to play in the GEMINI role here and ask Shivani to follow perhaps over chat because we are at the bottom of time here, and I want to make sure we have a chance for Karthik to present. I'll quickly double check. Karthik, are you online?
Yes, Brian. Yes, I'm here. Yeah.
Okay, great. Well, so then, as we've done in the past, I'm going to go ahead and stop this recording, and we'll start a new one for your session. And certainly I love the fact that there's more conversation going. So let's keep that going over the chat, and certainly by following up as might be appropriate. All right, so let me stop the recording.